Hi, this video we're gonna looking at boundary work. The we're talking about enclosed system. There's a rigid vessel. In that situation, there's no boundary moving. And however, for piston, there's a boundary work. When piston go down to compress or going up to have the air inside the system to be expanded. So now let's look at just some moving boundary work. Boundary work. Our goal is to find out what's the governing equation for that. So we know work is force times distance, right? So it's F times distance. So we use the piston as display here. The force times distance, ds is the distance it's moved. And this force is going to be the pressure inside times the cross-section area that give us a force PADS. Now let's focus on what's cross-section area times the ds. That's going to be the volume displacement, PdV. So here is the expression for boundary work. So it's going to be PdV integral from state 1 to state 2. That's our moving boundary work equation. So B indicate the boundary. That's integral PdV. All right. Then we learned in calculus, when you look at the integral, it's pretty much if we're trying to draw PV and we just randomly draw a curve, and the boundary work will be the area underneath the curve, right? That's basically essential of integral. It's the area underneath the curve. Okay, so now let's look at some special scenario. The first scenario is going to be if this is constant volume. What would be constant volume? In other words, for closed system, you have a rigid tank. Then there's no moving boundary. The boundary doesn't work. So that's a constant volume. Then we start with this equation here. Boundary work is going to be integral of PdV. And when we have no volume change, constant volume, this is going to be equal to 0. That boundary work is equal to 0. You can also, looking at a PV diagram, if it's constant volume, it's going to be a vertical line. And what's the area underneath this curve? 0. Okay, so boundary work is going to be 0 when it is rigid tank. Intuitively, we understand that's right? There's no boundary work. Then the second scenario, if this is going to be a constant pressure, then what do we have? Constant pressure scenario could be a piston that's going to be a constant weight. So in that situation, the substance inside have the same pressure. Then we start with this governing equation, PdV integral. And since pressure is a constant, we can take outside of the integral. So we have PdV going from state 1 to state 2. And integral dV, we're going to get to V. So we're going to have V2 minus V1 after integration. That's going to be the boundary work for constant pressure. So you see, with different scenario, you're going to have a different boundary work. For constant pressure, it's going to be P V2 minus V1. Now let's look at another scenario. If this is going to be ideal gas inside, okay, so that's the first condition. If it's ideal gas, and it's going to be isothermal process. So this isothermal could be isothermal expansion, increase the volume, or could be isothermal compression. Then what do we have? So we start with governing equation, integral of PdV. Since this is ideal gas, first of all, we can go ahead and change using ideal gas equation. PV equal to MRT, and that's big volume. So in that situation, I can see the P is going to be the pressure equal to MRT over volume. So we're going to substitute that P into this integral here, MRT over V dV. Now let's look at this integration. Is mass a constant? Yes. Is R, gas constant, a constant? Yes. How about T? Is T a constant? It is. Why? Because it's isothermal. When we talk about isothermal, that means what? Temperature is constant. So in that situation, all of here together, MRT, they are constant. We can take out of the integral. So we have MRT. Then inside, we'll just have 1 over V dV. Now let's continue to integrate that MRT. What's gonna be integral? What's the integration of 1 over V? We know it's natural log V, right? Then here it's from V1 to V2. Then put to the upper lower limit A, then we'll have natural log V2 minus natural log V1. Then using natural log operation, we know that's going to be V2 over V1. That's our boundary work for what condition? 2. First, have to be ideal gas. Second, have to be isothermal. Now let's expand this boundary condition expression one more time. How about this MRT? Using ideal gas equation, MRT is equal to PV. And if there was 2 states, state 1 P1 times V1 is going to be equal to MRT1, and P2 V2 is going to equal to MRT2. And be aware, they are equal. Why? Because it's T1 equal to T2, it's constant, it's isothermal. So in that situation, they all equal to MRT. We can get rid of the subscript under the T, right? In knowing that this MRT, because it's isothermal and because it's ideal gas, we can replace MRT with P1V1. We can also replace this MRT with P2V2. Right? All of those work. So all those are 3 expressions. They are interchangeable. When do we use which? Just be smart about it. If the problem gives us the temperature, go ahead using the first expression MRT here. If they give us some pressure, then go ahead using the later expression here. So that is the boundary work. Let's wrap it up. So boundary work, we know the Galvani equation is integral of PdV right here, and it's area underneath the curve. We're talking about if it's constant volume, there'll be no boundary work. That's equal to 0. And if it's constant pressure, pressure can be taken out. Here I'm going to add a PV diagram here. If it's constant pressure, it's going to be like that, right? Horizontal line. So the area underneath the curve is basically a rectangle. It's this P, which is height, and the distance here is going to be V2 minus V1. That's a rectangle area. Then the third scenario is have to be ideal gas and also have to be isothermal, knowing that after integration, we figure out that's MRT natural log V2 over V1. We can replace MRT with P1V1 and P2V2. That's all for this video. I'll see you next time. Bye.